Right, are they up?
Okay, cool. Good.
Shall I just launch?
Yeah, just go, I think. It's a pleasure
Okay.
to be in from the Grady Institute, who I didn't realize I was down as a co-author, but thank you. Yeah, she's got a great background in causality and in AI ethics, and yep, and is a great speaker, so thank you.
All right, so I think this is really just going to follow on from Philip's talk. It's just another way that you can represent the assumptions that you make when you draw a Pearlian graph. But if you wanted to do that within a fully Bayesian framework, and in this case, a probabilistic graphical model, so a graphical representation of that. And so I guess the goal was to try and help resolve some of this confusion around questions as, can we condition on all of the observed data? Can we condition on these variables? And can we do causal inference inside a fully Bayesian framework without anything sort of extra statistical? So that's the goal. So just some preemptive clarifications, because of this topic can be controversial. So firstly, please don't think that I'm claiming that causal inference is possible without assumptions. For that matter, very little inference is possible without assumptions. I'm also not saying that we should just throw away the do calculus and solve everything with Bayes' rule. And I'm aware that correlation is not the same as causation. All right, so I think following Philip again, the type of causal questions that I'm interested in and that I'm talking about here are the ones where you want to understand an intervention in some system. So these are the problems that Pearl would put on tier 2 of his ladder. We're talking about interventions. I'm not talking about things that involve the joint distribution over counterfactual, so these kind of weird philosophical problems. So putting those aside, I'm talking about these kind of problems where we've got one system and we've got some data sampled from that system. So for example, we might have the preschool system or the school system, and we could ask what's the average reading ability of kids who attend preschool under the current system. And then we say once they get to kindergarten. And then we've got this other system, which is related to system A in some way, because it is system A after we've changed it. And if we then want to ask a question about the system after the change, using the data that we collected before the change, so this is the kind of observational causal inference paradigm, then we're going to need to make some assumptions about how this system B is related to system A, because if they're completely unrelated, then the data we've already collected is totally uninformative about the question we want to answer. All right, so there are heaps of things that meet the definition of a causal model under that view. So we can build a simple physics model, and this is just a spring constant. We can say, I can use this to predict what will happen if I hang a 10-kilo weight off of this spring. I'm sure everyone's very familiar with these epidemiology models at this point in time. Again, we can use this model to predict what happens if we allow a disease to spread with no constraints. We can predict what happens if we lower the infectiousness rate or change the response rate, and so on. And finally, there are these Pearl-style DAGs, which again allow us to predict things as a consequence of a change. And all of these models are only going to work to the extent that the assumptions they encode hold. So, the spring constant model encodes a very specific assumption that the extension is going to be linear with respect to the force applied. Obviously, at some point, this assumption is going to fail when I hang a 1,000-kilogram weight of this thing. And similarly, this model is a simplification, and so are Pearlian models. All right. So when we come to the question then of, is causal inference fundamentally extra statistical? it really depends on what you regard as statistics. So if your view of statistics is that it's a set of operators like mean, covariance, etc., that can be applied to a matrix of data, then causal inference is extra statistical, because we need to kind of have this model of what's changing between two systems. But if we view statistics as the process of drawing inference about some potentially latent quantities we care about by combining a model of data with data, then causal inference just fits within that paradigm perfectly. We just need to model the change that occurs when we intervene, and that's part of our model. So then if we're thinking about this as the model likelihood, if you're going to subscribe to the second view, that you can do this fully within a statistical paradigm, then you need to make sure that you're modeling the intervention itself, not just the system pre-intervention. And as long as you do that, then there's nothing extra statistical about this problem. All right, so now let's look at the Pearlian style causal graphs. And they are much more general in some way than, the spring constant model, which relates only to springs and has a whole lot of very specific assumptions about the functional form and so on. Similar to the epidemiology model, that's very specified for a single problem. Whereas causal DAGs are a mechanism for specifying assumptions for a whole broad class of problems that you can frame in this way. And so I'm sure people are pretty familiar, but the idea is that you draw these arrows and think of them as saying that the one variable causes another. But in terms of effect, the important thing is that that leads to what Pearl calls the truncated product formula, or what happens when you intervene in the system, basically. So if we accept that this is the graph related to school readiness and attended preschool, and we think about these arrows as meaning cause, then what Pearl is saying is, okay, if we are going to intervene on this variable t, then the impact of that is that now t is just going to be set to whatever value we want it to be, and any arrows coming into t are going to disappear because we are now controlling t. And it's also assumed that everything else is going to remain invariant. So between these two graphs, the distribution over z is not going to change, and the conditional distribution of y given z and t is not going to change. So that's the assumption that's being made. And this is nice. It's quite an intuitive way, I think, for specifying what your assumptions are going to be about how the system changes. It doesn't require that you have any functional form in mind on these conditional distributions. And because this uses DAGs, it means you can use conditional independence to figure out what is going to be invariant between these two graphs, which is where the do calculus stems from, and which leads to this nice mechanism to translate some question you have about this system into an expression that contains only terms that involve the system pre-intervention, which is where your data comes from. So that's what you have to use for inference. So there's a lot of great reasons for doing this. And in particular, it leads to this identifiability question, which is, do we have sufficient invariances that we can compute the quantity that we care about purely in terms of distributions that are observable that are observed from the original data generating process. And if we can, then provided we have infinite data, then you'll eventually be able to converge to the quantity you care about. And if you can't, then even with infinite data, you can't infer the quantity you care about because you can't express it in terms of the data that you have. So that's pretty powerful, given that we haven't even specified any functional form. We've just thought about what arrows are going to go away when we intervene. All right. But then there's these two components. When you're thinking this kind of way, you construct your model with your assumptions about how the intervention will change the system, which in Pearl's case is which arrows go away. And then you've got to actually estimate the thing you care about from some finite data. All right. So suppose we did want to represent the same set of assumptions as were made in a particular causal DAG for a particular variable with an ordinary Bayesian probabilistic graphical model. So firstly, let's just explicitly make those assumptions. So our original system here, we've got M data points sampled from the system pre-intervention. And we're saying that the arrow that's going to go away is the arrow from Z to T. All right, and so we haven't observed either Z or Y star. These are the post-interventional ones. So these are the variables we haven't observed. Now we need to relate these two things together. So first of all, we're going to parameterize the distribution P of Z with gamma, and that's going to be the same because the assumption is that we're replicating the assumptions made by a causal graphical model. So we're just saying this arrow goes away, but everything else stays the same. So we also need to have a shared parameter representing the conditional distribution of Y given Z and T. And we can just, for completeness, we can parameterize T as well, but that's not going to matter because T is now going to be fixed to a constant in this in the post-interventional variable T star. And then we can basically write out an expression for our posterior over these variables that we care about, these V, which is the V star is the post-interventional variables, in terms of the parameters here and the data that we've observed. And this kind of factorization that we've made here, so we're basically saying you're going to compute, first of all, estimate the parameters based on the data, and then try and estimate this post-interventional distribution of over the variables, the starred variables, given the parameters and the value we've set for T. And this factorization is generally going to hold because the way that we've constructed this DAG, once you condition on the parameters, the V stars are independent of the data, and T is set exogenously, has no parents, and so it's also independent of the parameters and the data. So that's why we can do that. All right. And once you've done that, you can condition. Once you've made this DAG, now these arrows, you can change them around in the way that you can change around arrows in a ordinary Bayesian networks. You can't arbitrarily flip them without also changing the distributions, but you can do those operations if you wish to. It will generally make the representation more complicated, but in principle, there's now nothing special about these arrows once we've constructed this this joint network. All right. And similarly, we can condition on all of the variables, even when we're talking about a graph where if we were just to talk about the Pearlian graph, you wouldn't want to observe those variables. So for example, here, if we make this network and we just plug everything into the expression that we had before, then there's no reason not to condition when we're estimating theta on the data D, which can include this Z here, even though it's a post-interventional variable. And if we were working with a causal graph, we'd have to say we must not condition on that. The impact of conditioning on that is not the same as the impact of conditioning on it when you're working in a Pearl style graph. It basically integrates away, so we can condition on it, but it doesn't do anything. All right. So why bother with all of this? You could say that, the Bayesian representation has far more nodes. It takes much longer to draw than just the ordinary causal graphical model. If we just try and kind of crank the handle on solving that estimation problem, and estimating these terms, this P of theta given D, and then the other term, then we'll quite frequently end up conditioning on or marginalizing over latent variables that we didn't need to, because they don't have any impact on the component of the posterior we care about. And if we've got a complicated graph, then figuring out if we want to answer the identifiability problem, or we want to find a simplifying reparameterization which avoids marginalizing over variables that aren't going to have an impact, we still have to follow the basic mechanics of looking at conditional independence, which is really the same as the do calculus. Or you could make a version of it framed in terms of this new representation, but we haven't really gained anything, and we've arguably got a much more complex representation. So, I mean, the reason that we did this initially is that purely as a conceptual tool to try and smooth the gap between how these problems are thought about in causal graphical modeling and how you'd like to think about these things from a Bayesian framework, or specifying a likelihood and then estimating everything. But there are potentially some practical benefits too. So one is it makes it very straightforward to add additional assumptions, particularly if you've got functional form assumptions or assumptions about what the distributions over various variables look like. And that potentially means that you actually get identification of problems that are not identifiable non-parametrically. And it's not even, once you start adding parametric assumptions, it's not even trivial to know whether or not the problem is identifiable. And the other point is that doing this can help smooth the really stark distinction between identifiable and non-identifiable problems. So when we say that a problem is not identifiable, all it means is that we won't get a point estimate for the thing that we care about, even with infinite data. So there'll still be some uncertainty about the value, even with infinite data. But that doesn't mean that the problem is fundamentally unsolvable, because we may still be able to get an informative posterior about the thing that we care about. And that may be enough. So let's look at a specific example for that. So this is kind of stemming from Andrew Gelman's objections to the causal graphical model approach, the no true zeros problem. So here, let's assume that we have got an unobserved confounder, this variable u. Just for simplicity, everything here is linear Gaussian. We would like to know the impact of intervening on t on y, which in this case can just be represented by this parameter wyt. But this problem is not identifiable because of the presence of this unobserved confounder. So if we put some priors over these things and just crank the handle with MCMC, then we get out these really quite broad posterior values, although you do so they have still narrowed substantially from the prior, and that's because there's a strong coupling between these various components, and so even these pretty broad priors that I've imposed on the W's and also on the sigmas have provided some information and have meant that the data is now somewhat informative about our question. But not very, so we can't tell, for example, even the sign of this parameter wyt. All right, but now what if we are willing to assume that if we wanted to make this problem identifiable, we could just say, well, actually, I don't think you exist, let's cross it off. And then we could just very easily, the distribution is now not changed by intervention. And so we could just compute P of y given t, and that would be our estimate for wyt. But what if we don't want to do that because we don't want to say that these are exactly zero? Well, let's just put a prior to say that they are very small. So here's our original posteriors with our broad priors, and here is exactly the same thing, but now with much narrower priors on the confounding links. So we've now said that they have very small weights, We can see them being drawn here. And now we've got really quite a tight posterior for WYT. Now, the thing about this is the problem is still not identifiable. So if I ratchet up this D to 1 million, to 10 million, this density is not going to narrow to an absolute point around WYT, because there's still going to be some uncertainty coming through from what actually is the value of these two unknowns here. So even with infinite data, it won't converge to an absolute point, but it will converge to something that is potentially sufficiently narrow to be useful in a practical problem. So this seems like something that could potentially be useful. It's quite hard to do in practice because the kind of you can't just sample blindly over huge latent spaces. So I think if this was something that was to be generally usable to try and tackle problems where you want to introduce extra links that make a problem non-identifiable, but you're willing to put priors onto bound the size of those impacts, then you'd need more work on how to set up sampling tools and so on to reparameterize or find spaces in which to kind of almost marginalize out the latent variables, and so as to actually make this something that works in practice. So I suspect I've run way too fast, but that's really all I had to say. So I'll stop there and take questions.
Are there any questions?
Well, I do. All right, so Finn, so I guess there is this separation that I think in the paper is not made of identification versus estimation. And so, okay, you're dealing with that estimation problem, right? Which is you're developing a Bayesian estimator of the target quantity, which is the P of I do X in this case, or P of Y sub X.
So I don't know that there is necessarily a separation of identification in this approach, such a hard separation between identification and estimation, right? Because in principle, I can estimate something that's not identifiable.
You can, that's fine, but they are logically distinct tasks, right? So I think that's the main thing for us to make this demarcation between causal inference and Bayesian updating. So when you say, for example, in the second model, the second one, where if you, this one, it's a problem to condition on Z. When we say that, we are not saying it's a problem to do Bayesian updating using Z. What we say is that the target estimate, right, the function of the data that you want to estimate, is not the G formula, or it's not the backdoor formula. So the functional,
absolutely.
So that's the difference between identification and estimation. So the target estimate is going to be, it's not going to be the E of Y sub T, E of Y given TZ average over the marginal distribution of Z. It's going to be average over the marginal distribution of Z given T, right? In this case.
Yeah, absolutely.
So that's what identification tells you. So you can condition all you want to update the parameters, but when you're computing the target query, you should compute the correct quantity, like the correct functional. So what you're doing here is actually, I think, so for the debate or the panel, that was something that I was thinking about, which is what can causal inference bring to Bayesian inference, is exactly what already happens in frequentist inference, which is a focus on the functionals defined non-parametrically. So that's what you're doing here, for example. So instead of defining the target parameter as some like symbol of a Gaussian or whatever, you are defining as the post-interventional distribution, because literally what you have there is the post-interventional distribution, right? The star model.
Yeah, I mean, the whole point here is to represent exactly the same assumptions as you make when you build a particular causal graphical model, but within
you're literally computing the post-interventional distribution, because so if you have a Bayesian model, you have all the parameters, right? So for every time you sample there, you sample from the post-interventional distribution. So now you have you can sample directly from the target quantity and average over it, instead of trying to figure out what is the function. But the identification task is still separate from this, right? It's because unless you manipulate...
It can be.
No, it is separate. It's a logically distinct task, right? It's if you just put the prior and update the posterior, that's different from knowing whether your posterior will peak.
Sure, but right? Causal inference doesn't have to require both of those steps. Like I could say, well, I just don't care about identifiability. The only thing I care about is to what extent, how tight is my posterior around the thing that I care about, given the amount of data that I have. I have no concern whatsoever about what will happen with infinite data. Now, I think it is useful to think about identifiability because it helps you come up with potentially much more compact representations for problems. It tells you where there are limitations on where you'll get, but I don't think it's correct to say that the only way to do causal inference is first think about identifiability and then...
No, it's not the only way. It's the definition of causal inference. Like if you're not doing the identifiability analysis, what you're doing is just inference, like a statistical inference. You're just updating your prior.
Yeah,
you're not doing the... Yeah, go, Larry.
I just wanted to add a comment here, because I remember this issue came up in Andrew Gelman's blog a number of years ago. It was kind of a frustrating discussion about the word conditioning being used for two different things. And so I agree with what you're saying, Carlos, is that there's one question is, can you write a formula for the causal effect? And when you write it down using whatever tools you want, decision theory, do calculus, whatever, you may discover that that formula involves a conditional distribution on Z or not, sometimes, depending on the DAG. That's a completely different question, that when I'm doing data analysis, should I be conditioning on the data or not, which is, the Bayesian thing.
Yeah, should I update the gamma or the phi using the whole data? Yeah, for sure. Maybe yes, maybe no. In the Ritov sense, maybe no, right?
Right. But and that's right. And so the question of what is the correct formula for the causal effect has nothing to do with data analysis or Bayes whether a Z or whatever appears in a conditional statement is a completely different question than that's just writing down a formula as opposed to how you analyze the data. I think there's a distinction there that sometimes gets lost.
Yeah, and that's for me, I think the Ritov example, because I think maybe I'm not a pure Bayesian. I'm not sure if I'm Bayesian yet too, but because when I see it, I'm saying I have this functional, now I can estimate however I want, right? Like maybe I can do some priors on it or whatever, but it's separate from the identification.
So I think there's definitely two. So identification as meaning the answering the question of can we get an answer with infinite data? That's one thing, right?
Also bounds. Can you get bounds with, like, we will get bounds with infinite data, for example? How tight will the bounds be with infinite data? So in your example with Gaussian, I can actually give you an exact answer for the sensitivity.
Right.
So you have the unobserved confounder, right? I can tell you exactly.
What if I put in a non-linearity there?
Yeah, I mean, the confounder could be whatever, as long as you want to estimate a linear regression. I can say, regardless of what is the dimension of this confounder, if we bound how much variance that explains of Y, I can tell you how much you would change your regression coefficient, for example.
Yeah, that's right.
So that's what I would say. It's at the causal inference part. Now, if you want to put priors and do the posterior, that's okay. But we have this deduction part, I think, which is the causal inference part of.
So I would argue that like the causal inference part is the part where we specify what the relationship is between these two sets of variables, the set of variable we've measured and the set of variables we actually want to ask a question about. So to me, the causal inference part is where we specify the assumptions that tie those two things together.
No, that's the causal modeling, right? Not the
Yeah,
inference.
but there's nothing fundamentally special about this than there is when we build a model of anything else.
Yeah, the question is, can you answer questions about the model? So if I ask a question like, is it identifiable? Or if not identifiable, is it bounded?
So I don't think that fundamentally being able to answer, I mean, I think it's useful to be able to answer those questions, but if we come back to what is causal inference, and I'm saying it's my ability to predict something about Y star, basically the system after intervention, given the data I've observed, then it's not a fundamentally necessary component of causal analysis that I can tell you what will happen with infinite data.
Yeah, but that's not causal inference. If you just have a model and do your posterior, that's just Bayesian inference traditional. It's like you're not answering any of the causal inference questions that we answer.
If I can answer what happens if I intervene in a system, I'm answering a causal question.
Yes, but that's not the question that we are asking in causal inference.
Okay, so you've defined causal inference as the set of problems that involve questions about identifiability. I've defined causal and identification. I've defined causal inference as a set of problems where you care about what happens after an intervention. So
a randomized trial, which there is no, it's not causal inference, it's just statistical inference. I have a data.
Yeah, I think
it's like Philip, I think Philip, do you want to jump in? Because Philip, in his slide, he said there is no inference here. I have interventional data and I'm doing interventional quantity. So
it's easy. I agree.
No, it's not. It's not easy. It's not. There is no inference involved. There's just a statistical inference from sample to distribution.
I mean, I think there's just statistical inference everywhere here.
No, the statistical inference is the jump you make from the data to the population, right? And the causal inference is the jump we make from different distributions. And then the analytical tools we develop to understand these jumps is the causal inference tools, right? And it's like a debugger for you to understand what is going to happen with your model. So it's like a posterior predictive check, but you don't even need the data to do that. Because you can tell beforehand what's going to happen to your model, even without the data.
Sure. I guess this is now purely definitional. What do we think causal inference encompasses? Is causal inference the process of answering identifiability questions, or is causal inference dealing with a set of problems where a system is changed and we want to predict the outcome? If you're talking just about identifiability, then
yeah. So for example, well, I guess we are in the panel already now.
Maybe we should give other people a chance. Yeah, exactly. But I mean, in a way, it's not bad because we're running a little bit ahead and we're waiting for the last panelist. But would anyone else like to throw in a question? Or you can go back to it if
I mean, I guess I can expand on this, right? So you're saying, okay, randomized experiments, there's no inference happening there because you're just going from the same distribution as
there's statistical inference, not causal.
Sure, statistical inference, no causal inference. So what about we move to more complex systems where there is a kind of interesting mixtures of experimental data? Recommender systems, for example, there's a certain degree of randomness there, but it's not entirely random because it's driven by a model. Do you regard that as causal inference or not?
Well, I can't, let me see if I can I share the screen? No, I can't put what I think it's causal inference here.
No, I can stop mine.
Well, I can say maybe. So I guess we have 3 inputs for causal inference, which is what do we want to know, and we need new notation to represent that, right? Either the notation is going to be the forcing node or the counterfactual or the do, and what we want to know is going to be a functional of the causal model, right? So it's a function of our causal model. And then what data do we have? And then do we have observational data, experimental data, under what conditions, selection bias? So we also need new notation to represent this data set. Either it's going to be, so for example, there you're representing with stars because you only have one type of data. But if I start giving you different types of data, how you're going to systematically represent those different types of data, right? Like, so someone can see that data and know exactly where it came from, right? Like, oh, this was intervened on this data, this was intervened on this data, without giving the graphical model, just by the syntactic representation of the query, right? Of the probability that I'm giving you. So for example, it's going to have an F node and you're say with set X equal little x, or it's going to be a counterfactual distribution or a do. So and then what we know is the model, right? It's like what invariance assumptions are we making? And then the causal inference part is going to tell us it's the deduction, right? Whether the data we have, what we know, is sufficient to answer what we want to know. And then sufficient could be point identified or bounds. And if it is sufficient, ideally, can we have a closed form expression for this? And other logical implications of our model, like does the model entail any testable implications and so on. So these are the types of tools that we are doing for the causal inference part of the model. Then when you come to the estimation, you can do Bayes or frequentist. And if you do Bayes, you could do exactly like you're doing, which is manipulating the model and then just sampling from the interventional distribution for the estimation. But now you understand what's going on there, right? Like, so you know what you're sampling and what is driving the results.
So I guess I don't think there's anything fundamentally special about causality that means you need to define a model. Put it that way. So you absolutely have to define a model. And, you know, like, I mean, going back to the examples of the spring, right, or the epidemiology model, from my perspective, those are also causal models because they predict the outcome of interventions, even though they're not DAX.
But how do you, for example, how do you non-parametrically define a causal effect?
So, I mean, that's not a essential component of the broad class of problems of inferring the impact of an intervention.
How do we even ask the question, right? Like, I want to get the, so for example, I want to get the distribution of a joint intervention where I intervene on X and Z. And the data that I have comes from intervention only from X, only from Z, and maybe also observational data. So I have 3 different types of data sets. And what I want is...
So then I'm going to need to write down in some way or other what the relationship is between those 3 data sets.
No, I'm not talking about the model. I'm just talking about how do you define these quantities, like the data that I have and the quantity that I want.
So I don't need special notation for that in the same way that I don't, like, if I want to talk about modeling a spring constant, you know, are you saying how I have to define the distribution before I add the weight to the spring and after I add the weight to the spring with special notation?
No, I'm just asking, how do you define these 3 different distributions? For example, I want to know the joint effect of X and Z on Y. And I have data from an experiment where I only manipulated X and data from another experiment where I only manipulated Y or Z. So I have these 2 data sources and this query.
So what I need to do then is I need to write down what I believe.
I'm saying, how do you write the query and the data sources? How do you express them? Like, I have this source of data and I have this query.
In a fully general way, I'm going to have to basically write that in words. I'm going to have to say, I've got this data that comes from this system and this data that comes from this system. And I want
words.
To refer, well,
so like, what you're saying is that you don't want to mathematize causal
If I
inference.
wanted, no, you can mathematize it, but you have, in order to mathematize something, you're going to need to narrow the assumptions you're making. So you can only jump to a DAG once you've made a whole bunch of extra assumptions. So
We're not talking about model specification. We're just talking about defining a quantity. So for example, Larry, in Larry's presentation, he said, we have this functional. The functional was an expectation of a conditional expectation over a marginal distribution, right? And we can define that for any marginal distribution.
I can define it this way, right? I've got multiple systems, and they're all separate variables at this point because we haven't yet specified a model to connect them. So I can just say, so you've got system A, Z and X, system B, T and Y or whatever, right? So I can just say, all right, I want to infer the distribution over these variables from system C. I could name them like Z star and T star to help show that there's going to be some connection, or I could just start naming variables at A until I run out of variable names, right? And I can write down mathematically, I want to infer P of, UX given P of A, B, and P of CD. Done. But in order to actually make any progress, I'm going to need to connect those variables together in some way. And I could do that using DAG assumptions and conditional independence. I could do that in some very specific problems by writing down some functional or differential equation between them. What I'm going to do to connect them together is going to depend on what assumptions I'm willing to make.
Then you're going to need to write a dissertation for every problem, for a very specific problem.
Okay.
Instead of solving automatically like we have now. Like we have complete solutions to all these problems. You don't need to write the whole thing again and have a informal way of handling the problem every time you need to solve the problem.
Okay, maybe we should wrap up. Thanks for all the discussion. I think the panel is going to be fun. We've just got